Hello. In this video, we are focusing on functions with several variables, particularly the study of critical points of extrema of the Hessian matrix of a function with three variables, how to characterize positive definite matrices, and what are the tests that allow us to determine if a matrix is definite. Positive. As a discussion support, we will consider the following exercise. Consider the function with three variables, x, y, z equals x2 plus y2 minus xn minus xn minus vn plus g 1/3 z. Determine the critical points, the extrema, and any saddle points of f. So let's start by recalling that in the study of extrema, we generally use Taylor's formula. If we consider a function of class C3 on an open set U of R3, we take an equal to 3 here, which is sufficient for our exercise. The Taylor formula of order 2 is written as follows. F of a plus h equals f of a plus the sum of the products of the first partial derivatives of f at a by k, ranging from 1 to 3, then k are h1, h2, h3, the components of the vector h plus 1 over factorial 2, the sum for I ranging from 1 to 3 times the sum for j ranging from 1 to 3 of the second derivatives of f with respect to xi xj at point A multiplied by hi j plus a third term involving the third derivatives, but at the point a plus th with th strictly between 0 and 1. So the third term, that sum, is just a dot product between the gradient of f at point A and the vector h. So we have the gradient of f at A dot product h. It's the gradient vector whose components are the partial derivatives. First derivatives of f with respect to x1, with respect to x2, with respect to x3 at the point A. Dot product, the vector h with coordinates h1, h2, h3. The fourth quantum, which involves the second partial derivatives, can be expressed in the form H transposed, which is a raw vector multiplied by a matrix H formed of the second partial derivatives multiplied by a matrix H by the vector H. This is presented in the following form. H transpose times H over times H equals the transposed vector of H times the sin matrix formed by the second derivatives of f at point A multiplied by the column vector H of is the sin matrix of f at point A. So to begin the study of extrema, we first need a necessary condition. To have an extremum at a point A, this point must first be a critical point or a stationary point. It is a point where the first partial derivatives are 0 or the gradient is 0. So we will start by looking for the critical points of f, or the points where the first partial derivatives of f are 0. Let's take f again. x2 plus y2 minus xy minus xz minus yz plus 1/3 z cubed. The first partial derivatives are the derivative with respect to x is 2x minus y minus z. The other terms have a 0 derivative with respect to x, so 2x minus y minus z equals 0. The partial derivative with respect to y is 2x minus y minus z. It's minus tot x minus z. 2y minus x minus z equals 0. The other terms have a 0 derivative since they do not depend on y. F's derivative, PRT has minus x. minus e plus 3 over 3z2 or plus z2. So it gives z2 minus x minus y equals 0. This is essentially about addressing this system. We see that we have minus e, which appears twice, and 2y. Minus x, and 2x. So if we think about doing the set of three equations, x disappears, y disappears, and there remains an equation where only z appears, which is z squared minus z minus 2z, which we put in the form z factor of z minus 2, which gives us z equals 0 or z equals 2. For z equals 0, if we substitute into the third one first, will be verified since the sum of the three equations is 0. If we substitute into the first two equations, we will find when z is 0, 2x minus y equals 0, and 2y minus x equals 0, since z is 0. Then by multiplying the first by 2 and adding, y disappears. And we find 4x minus x, 3x equals 0, which gives us x equals 0. But by substituting into one of them, we also have y equals 0. Thus, we find 0, 0, 0 as the first critical point. If z equals 2x, when substituted into the first two equations, we obtain 2x minus y equals 2y minus x equals 2. And by multiplying the first by 2, by adding the second, we find 3. X equals 6 or x equals 2. And by substituting, we have 4 minus y equals 2. Thus, y equals 2. And so we find the critical point of 2. Once we have found the critical points, we need to determine if they are extrema or saddle points. For this, we will return to the form. The Taylor formula. When the gradient is 0, the Taylor formula already starts with 1/2 h, transposed h over h plus, the third term which depends on c. In this formula, the difference f of a plus h minus by f of a is determined by the sign of this first term, which dictates its sign. So this term there depends on the hcn of f phi at point A, h of A, and we have a sufficient condition for having an extremum, which states if the Hessian matrix at point A is positive definite, then F has a local minimum at point A. It remains to be seen if it is global. If the Hessian matrix H of A of F at point A is negative definite, then F has a local maximum at point A. And if the difference changes sign around 0, then F admits a saddle point. Therefore, we are now led to calculate the Hessian matrix at the critical point and determine if it is positive definite. Let's start by calculating the Hessian matrix at the first critical point, 2, 2, 2. So we take the partial derivatives here to calculate the second partial derivatives, seconds. We see that the second derivative with respect to x2 is 2. The second derivative with respect to y and x is minus 1. And the second derivative with respect to x and z is minus 1. There's no need to look for the others, that is, the second derivative with respect to x and y, since they are equal due to the fact that second derivatives being continuous, the mixed derivatives must be equal according to Clairaut's theorem. We now have the second derivative with respect to z and y, which is minus 1. The second derivative with respect to y, we differentiate with respect to y twice, we find 2. And finally, if we differentiate with respect to z twice, we find 2z. We are here at the critical point, 2, 2, 2, so z equals 2. So the last derivative is 4, and the matrix at point A, 2, 2, 2, and the matrix 2, minus 1, minus 1, minus 1, 2, minus 1, minus 1, minus 1, 4, which is a symmetric matrix. We therefore need to know how we are going to determine if this matrix is positive definite. For this, we have a characterization called Sylvester's test, or the principal minors test, or the determinants test. So, what are the principal minors? I remind you. If we have a matrix, A equals 1, 1, 1, 1, 1, 2, etc. We will take the AI matrix formed by the first I rows and the first I columns. For example, A1 will be the matrix formed by a single element, first row, first column. A2 will be the matrix formed by the first two rows and the first two columns. So it's A1, 1, A1, 2, A2, 1, A2, 2, and so on. So the principal minors are the DIs defined by DI equal E to the determinant of AI. In this case, D1 is the determinant of the first matrix formed by the first row and the first column, which is A11. D2 is the determinant of the matrix formed by the first two rows and the first two columns. And D3 is the determinant of the entire 3x3 matrix, 3 rows and 3 columns. The minus test states that A is positive, definite if and only if all the principal minors are strictly positive, and A is negative, definite if and only if, for any I between 1 and n, negative 1 to the power of I times di is strictly positive. Therefore, negative 1 to the power of I depends on the parity of I. This test means A is negative, definite if and only if D1 is negative, D2 is positive, D3 is negative, depending on the parity of I. In our case, the hessian matrix that we calculated, we will apply the principal minors tests to it. D1 is the determinant of matrix 2C2, and it is strictly positive. D2 is the determinant of the matrix formed by the first two rows and first two columns, C41, C3. It is strictly positive. D3 is the determinant of the entire matrix H, equivalent to 2 times the determinant 2, 2, 1, 1 to 4, minus 1, times the determinant 2, 1, 1, 4, and minus 1 times the determinant 2, 1, 1, 2. This indeed gives us 2 times 2, 8 to 1, minus 1 plus minus 4, minus 1 plus 2. So this certainly gives us 8 minus 1, 7 times 2, 14, minus 5, minus 3, or 6. It is strictly positive. So the principal minors are all strictly positive. The Hessian matrix of F1.1 is positive definite, and thus F admits point A admits a local minimum at point A. Now it remains to determine whether this minimum is local or global. We have the value of the minimum F of 2 is equal to minus 4/3, and we see that if we calculate the value of F at the point 0, 0, minus 2, we find minus 8/3, which is less than the image of 2, 2, 2, and consequently this minimum is not a global minimum. Now let's move on to the study at the critical point 0, 0, 0. In this case, the matrix had 2z in the last position, so it is now 0. If we calculate the principal minors, we redo the calculation. The first two are the same, strictly positive, but the third D3 is equal to minus 6. It is negative. We can see that H is not positive definite. Since D1 is not negative, H is not negative definite. But we cannot conclude from this, as it is only a sufficient condition. So what to do to know in the case of the critical point 0, 0, 0, if we are facing an extremely minor point of the scene? We return to the quadratic form that gave the sign at the beginning of the Taylor expansion. There was a half, we will do without the half. We will study the sign of H transpose times H over times H when H is close to 0. So in general, the calculation of this quadratic form is written in this form. A term in H1 squared, a term in H2 squared, a term in H3 squared, and the cross products. In general, we try to write it in the form of a constant times a square involving h1, h2, h3 plus a constant times a square involving h2, h3 plus a term in h3 squared. If the coefficients a, v, g are strictly positive, the quadratic form is defined positive. What about in our case? We are at the point 0, 0, 0. Here we have the Hessian matrix. If we calculate Q2H, we find by multiplying the matrix by this vector, then this vector we obtain, the column vector, multiplied by this row vector, gives us the following scalar. So when simplifying the calculations, we can group the terms in H1 and leave the others aside. The terms in H1, by factoring out 2, we can here see the beginning of a notable identity of the form RBC2, which we know from which we derive A2 2AB 2AC. This allows us to write that A in the form 2 times H1 minus 1 half H2 minus 1 half H3 squared plus 3 halves H2 squared minus 3 H2 H3 minus 1 half H3 squared. At this level, if we factor out 3 halves from these two terms, we have the beginning of a square. And if we compensate, we bring it back to 2 times 2. H1 p minus 1 half H2 minus 1 half H3 squared plus 3 halves H2 minus H3 squared, and we are left with minus 2 H3 squared. The calculation is extremely simple. This form, we see that if we place ourselves on the line, H1 equals H2 equals H3. With H1 at 0, we obtain the second square 0, the first square 0, and the expression would be due to minus 2 H1 squared there. It is minus 2 H1 squared, which is negative. So on the line D1, which passes through the critical point, 0, 0, 0, the quadratic form is negative. If now we place ourselves on the line, H1 equals H2 with H3 equals 0, it's a line that passes through the origin. We have Q2H1, H1, or equals 201 squared, which is positive. And consequently, we have here two lines that both pass through the critical point. On one, Q is negative, and on the other, Q is positive. It is therefore a saddle point. Thank you.